AP Chemistry, this is the answers video for day 106 on weak bases. So what is a Kb value? A Kb value is the equilibrium constant for a base reaction. It's what you need to use if the reaction is a base reaction, and you'll learn just through a little bit of experience what the base reactions are. Many problems will give you a Ka value, and you can look up Ka values in books and on the internet, but you can't look up Kb values. So what do? So you simply use the formula Kb Kb equals Kw over Ka, and of course Kw is 10 to the minus 14th power. Okay, it's the auto-ionization constant of water, and that's how you would get it. Okay, what are the conjugate acids of the following? So that means these are bases then, and they're going to gain a proton to become an acid. So this is going to be NH4 plus because it gained a proton. And finally, this one, you add another H. So it's C5H6N, okay? Write the long form equation for the following bases in water and long form generic equation. Okay, so it's asking for two things here. Characteristic of a base is that it produces hydroxide ions in solution. And there's the conjugate acid of ammonia. It's the ammonium ion. Okay, it asked also for long form generic. So since this is this is an electrically neutral base, we're going to use B. If you used A minus, it really doesn't matter. As long as you get the numbers in there correctly, you're fine. So you're taking the conjugate base and you're adding a hydrogen to it. So you just call that BH. And of course you show the hydroxide in the water. Okay. These are all weak bases, so they're double arrows. This time we'll use A minus since it is a negatively charged base. Okay, and this one will have to come on down here a little bit. If you're wondering which of the hydrogens gets that extra proton, it's never one. A base and acid are never attached to a carbon. They're always attached to either a nitrogen or an oxygen. Okay, so that's what this one would look like. All right, so study those. Be sure you understand those. Let me put some lines in between these. There. Okay. Okay, compute the pH, the big 4 here for 3.2 molar of C5H5N. We did this in class. Let's go ahead and do it again. Start initial concentration. All coefficients are 1. We're really interested in this, what this turns out to be, what that value of X is. And it does give you a Kb. You got to be careful it's not a Ka. Okay. Okay, so this is the value of X. So that means the hydroxide, which is what we're really interested in, is that value right there. So we'll go ahead and calculate our 4 values that we're looking for. Again, the thing to remember is that this is a hydroxide, not a hydronium anymore, because it's a base reaction. And now you're calculating a pOH. Okay, so pH above the number 7 is a base, and so this is well above 7. Not a strong base, but it's a base. Okay, very small number. It's a basic solution, so there's very few hydronium ions in it, okay? And students are constantly asking me how many places, just a couple places after the decimal. We're not going to worry about significant figures. Let's focus on this subject here. Okay, so there are the answers for that. Okay, next is problem 4 on page 4. So now you have ammonia, same kind of ammonia people use for cleaner. And there's the Kb for it, so let's go ahead and write that one out. And that's your hydroxide ion concentration. Okay, and that's all of the different variables we're looking for. Okay, now we're going to do the same reaction. This is number 5 as we just did, except now we're going to introduce a common ion of 1.4 molar ammonium chloride. So let's write out what that is. Ammonium is NH4. It's a positive charge. Chloride is a -1. You should know that by looking at your periodic table. It's in the halogen group. So if you put this +1, -1 together, it's a neutralized conjugate acid here. Okay, and if you look at your solubility rules, it's not one we deal with very often. This is soluble with everything. Okay, look at the upper left-hand side of the solubility rules. You see NH4 there. So what that's going to do is it's going to break one way. It's not reversible into this and that. Think of this as the pre-reaction. This does not go down here anywhere. This is the pre-reaction. Just think of this as happening before the main reaction that we're about to do here. Okay, so what we know is if we put 1.4 molar of this into the solution, we're going to end up with 1.4 molar of the ammonium and 1.4 molar of the chloride. Now we don't care about the chloride, it's a spectator. We care about this because it's the common ion of ammonia. So ammonia as a base produces ammonium ions, and this produces ammonium ions. So that's what we're interested in, is this. That's going to go down here. So let's go ahead now and do the problem exactly the same way, except we're going to have a starting concentration of ammonium. Okay, just to save time, I'm going to skip and go straight to writing with the variables, not writing with the equation, which you should really do. So let's go ahead and do that. And there's the KBs, the same as the last problem. Okay, simplifying assumption, we're going to assume X is very small compared to either 1.4 or 2.6. It would have to be small compared to both. We're going to say that it is. And that is our hydroxide concentration. Okay, so there are all the concentrations. Okay, explain the difference between the pH of problems 4 and problems 5. So let's do that. So the pH, okay, so the pH in problem 4 was 11.84. So this is a much less acidic solution. The closer it gets up to 14, the less acidic and more basic it is. In the last problem, you got one that was less basic, and it's still a base, no question about it, but it moves in the direction of acid because it's a lower number. So this is lower, more acidic. This is a higher number, more basic. So why did this one become less acidic and more basic? Okay, let me keep it straight. Why did problem 4, why was it more basic and less acidic, and this one was more acidic, the current problem? It's because The common ion makes this side of the equation more crowded, so the reaction doesn't flow from left to right as well because it already has concentrations over here. Now, clarification on Le Chatelier's principle. Favoring reactants does not mean the reaction is going to go back towards reactants. That's why they use the word favors reactants. It means it's moving more in the direction of this, or put it another way, it's moving more slowly in this direction. So this reaction with the common ion will still go from base to acid, from left to right, but not as quickly. Again, why? Because you have this concentration, and so it can't move as far over here. And if it can't move as far over here, this is really what we're interested in, it can't produce as many hydronium ions. So it's not going to be as basic. That's the pH of 9.52. Okay, without this, then the reaction can more freely move over here, create more hydroxide ions, and become more basic. And that was the last reaction of 11.84. Okay, so think about that explanation. Again, it cannot move as well with the common base as it would without it, so it cannot produce as many hydroxide ions, so the pH is not going to be as basic. It's not going to be as high a number, close to 14. Okay, on to question 6, and you got 2.6 molar of methylamine is placed in aqueous solution. There's no common base here, but you don't know the formula for methylamine. So this is where you would use the generic notation, and we're going to go ahead. It doesn't matter whether you call it A minus or B. It really doesn't, as long as you get the numbers right, and you're going to end up with the same hydroxide concentration. Okay, but let's call it B. It's just some generic base. You added the proton on to that, and if that's the case, and I didn't show this earlier when I told you about this, you'd put a plus sign there because now it's a positively charged. It's like ammonium, NH4 plus. All right. Again, I'll skip ahead past this. Well, let me go ahead and write it with this because it's generic notation. Okay, they do give you a KB, not a Ka. Be careful of that. You don't have to make the conversion. Don't worry about adjusting the decimal until you've gotten to your final answer. Just leave it like this for now. Okay, so this is your X value, so that's your hydroxide concentration. That's a fairly big number. That might not pass the 5% rule, but we don't care. We're just going to go with it here. A very high number for pH. That means it's way up in the basic range, very close to a strong base, maybe not quite. So that is the answer to that. Okay, final problem number 7. So concentration of methylamine. Now they give you the formula, and the reason is because you have a common ion here. So the conjugate acid, that means you add one proton to this to make it this last one H3. When you do that, it makes it positive. So let's write the pre-reaction again. That's my name for it. I just think of it as happening before you start the acid-base reaction. Okay, so it's going to be this one, putting this in the solution first. You don't have to put it in first. It doesn't matter what order you put things in. It will come out the same. So if you add a proton to this, you want to neutralize it. You can't buy chemicals as positively charged or negatively charged ions. They have to come neutral. So this would have a positive charge to it eventually. We'll show that here in a second. And then you put the Br, which is a halogen, so it takes on a 1- charge. So this is neutralized. It's electrically neutral. So we're going to do this. So now it has a positive charge because the bromide is going to dissolve off. And that's a Br minus. So that's a plus sign. Let me write it a little clearer. Now, with methylamine. So methylamine takes a proton from water and makes this second hydrogen go from 2 to 3. Again, the proton is never going to jump on carbon attached to hydrogen is never going to be an acid base. It's always going to be nitrogen or oxygen, okay? So there you go. And now it has a plus charge because you added that proton. And then the characteristic of any base is it's got to have hydroxide, okay? So now we're ready to start filling in the numbers. And we have an initial concentration. And it said that it was 1.2 molar of this. 1.2 molar of this is going to produce 1.2 molar of this conjugate acid and 1.2 molar of the bromine, which we don't care about. Okay, so this is the number we're interested in. All right, and now we just proceed like we have in the past. And I'll skip over writing the equation form, just go straight to the variable form. Oh, I said I was, and I didn't. So let me just finish it. What the heck? Okay, now I'll do it. Okay, so now we're going to get rid of these x's. Addition, subtraction, not this one. You can't get rid of that. I'm going to go ahead and divide all in the same step by the 1.2. Put that down on the bottom of both sides. And it cancels there and there. So now you just have that x all by itself. 2.6 times 5.6 divided by 1.2. So that's the hydroxide ion concentration. So we go ahead and just fill out down here. Okay, so again, the question about how the pH compares in this problem, which is 11.08, and in problem number 6, the previous problem, it is 12.56. So this is more, it's still a base, don't get this confused. It's still more acidic. It's moving in the acidic direction, meaning lower than this. So this is more basic. Okay. In number 6 in the previous problem, why? Because in the previous problem, you didn't have the common ion, which meant that this reaction could flow more freely to the right and create more hydroxide ions, which is more basic. Okay, and that's what you got here, 12.56. In this one with the common ion, the reaction could not flow as freely because you already had this side of the room a little bit more crowded, so you could not produce as many hydroxide. Therefore, it's not as basic and it's more acidic, so you got a lower pH. All right, that takes care of this answers video.